Okay, friends, so let's get in here and change out this information. We're not talking about COVID anymore. We're talking about does the fish have too much mercury? I'm feeling fancy. HG. We gotta make this fit a little better. Oh God, I'm making it worse. All right, you know what? The hell with this. Does the fish have too much HG? There we go. And then how did the fish test? Okay, because it's going to be positive, negative, and yes or no. Those aren't going to change. What's going to change is these rates over here. So I just said we're going to make it 50% infection rate. The false positive rate is 4%, so I can leave it at that. And the false negative rate is 0.01. All right. In order to calculate the probabilities, and I'm feeling really good about these because look at how large the green boxes are compared to the pink boxes. That's pretty fabulous. So I think what we should do, since I'm going to be asking you to do a lot of calculations about the chance of having or not having a disease based on results, let's actually kind of goof over here to the side and let's create the probabilities right in Excel. Chance you have it assuming you test positive. Now the reason I'm being very vague with that phrase is because we're going to use this for more than just the fish. We're going to also use this for lots of applications here. So I'm trying to make it as generalized as I can, if that's okay. All right. So chance we have it, assuming we test positive. Well, like we did before. Before I get to the function, that means we have to have it and test positive, and then divide it by all those that tested positive. So I vote we just do equals that number divided by, now watch this, parentheses, that number plus that number. Make sure you don't forget those parentheses. And that's going to be a nice high 96% chance. Boom. Change it to a percentage if you want. We can make it bigger. We can bold it. You can add some background, whatever you want to do. Not black, though, because you can't actually see the damn thing. All right. And then we're going to do down here, how about the chance we don't have it, assuming test negative? Make that fit. Change the fonts here. Assuming test positive, assuming test negative. Yeah, I don't like some of my capitalization is a little lacking. I apologize. It's late Friday afternoon. My brain's shutting down. I'll make it a little bit different color too. Okay, so this is going to be similar. We're going to take, we don't have it, so we tested negative. Assuming test negative. If we tested negative, these are the folks that don't have it, or the fish that don't have it in this case, and then we're going to divide that by everybody. All right, so there you go there. We can make that be a slightly different color, I guess. Bold it. Change it to a percentage. Change the font size if you want. Okay, so what does this tell us? It says, well, if a fish tests positive for too much mercury, there's a 96% chance they actually have too much mercury, which means there's a 4% chance they don't. And if a fish tests negative, then there's a 99% chance that they are clean, which means not too much mercury, which means there's a 1% chance that they actually do have too much mercury and the test missed it. Now, some of you might be thinking, Sean, why do we even have to go through all this? We knew that over here. Well, there's a couple reasons why you can't just look at this and bypass all of this. And the first reason is that these numbers aren't exact. If we actually throw ourselves some more decimals, they're not exactly equal to 96 and 99. They're equal to 96 and some change and a little bit less than 99. They're close, but they're not exact. And the reason that they're close but not exact is because you actually have these extra little boxes in here. It becomes more obvious when you change the incidence rate. Now, I know we're assuming that it's 50% in the lake. Let's say we make at 25%. Let's cut the incidence in half. Well, that changes the probabilities over there considerably. It just made the chance of a clean fish, assuming a negative test result, go up. And you're going to see that if you keep changing the incidence and keep making it go closer and closer to zero, that probability will continue to go up. And that should make sense, hopefully, because this number keeps going down because the number of fish that are sick in the lake is going down. So, you know, you go to 10%, you go to 5%, you go to 2%. This chance is getting closer and closer to 100%. The problem is the chance of a fish actually having the disease, assuming it tests positive, drops significantly. And that's because the two numbers are related. They're not inverse. I know that as one went down, one went up in this particular case. But all of these numbers are based on these three parameters over here: the incidence rate, the false positive, and the false negative rate. This number up here is irrelevant. You could use 10,000 as a base. You could use 1,000,000 as a base. It doesn't matter because this is all based on ratios. I mean, yeah, the raw numbers are changing, but the ratios are not over here. But these three parameters control everything. And that's what's so interesting about this is called Bayesian analysis. It's so cool to be able to get in and actually mess around with the assumptions. Now, you're placing an awful lot of faith in these three numbers over here, and that's the catch. You got to make sure you're right about this, because let's say you're off by the false positive rate. Let's say it's actually only 2%. Well, that's going to have a significant difference on your results over here. And let's say you're off by the incidence rate. Let's say the incidence rate is actually, 80%. Okay, that makes them both shoot off almost to 100%. So you have to be really sure about the numbers that you're getting in the analysis. But once you do, it's not a problem. This is bomb-proof mathematics. All right, go try some more.